All right, this video is going to go over pages 23 through 25 in your sound waves packet. So we're actually going to talk more about refraction now. Okay, so refraction, remember, that is when we have the bending of light as it moves into a new medium. Now, when it changes medium, it will change in speed, direction, and wavelength. Okay, but a key thing here is that frequency will actually stay the same. So we look at our equation, V equals frequency times wavelength. Okay, so the question's been is, well, normally we said if wavelength goes up, frequency would have to go down. Well, that's if it stays in the same medium. If it stays in the same medium, that means this velocity right here isn't changing at all. So if wavelength has to go up, frequency has to go down. But as soon as you change a new medium, now the velocity has to change. So that means something has to change with it and something has to stay still. Okay, so velocity here is going to change, and then wavelength is going to change as well. Okay, frequency is dependent upon the source. Okay, so basically whatever is emitting that frequency, it'll stay that frequency when it ever enters a new medium, but wavelength will change, the velocity will change, and the direction of the wave, meaning it's going to bend, so it's going to change its direction up a little bit there. So what we're going to do is we're going to draw a few scenarios. Okay, so I'm going to do is I'm going to draw a surface. Let's just say this is a air. So we'll just say air, and this is water. Okay, so this is going to be a less dense on top and then more dense on bottom. Okay, so I'm going to change up colors a little bit. Okay, what you have normally is, this is called a normal line. Okay, so your normal line is what helps us determine our angles when they come in and when they bend whenever they enter the new medium. Okay, so let's say we have an incident ray. Okay, so this is our incident ray. Incident basically means incoming. Okay, so this is our incident ray, so incident. Okay, or you can label it lowercase I. Okay, now your incident ray is going to come in, it's going to hit that water surface, and then some of it's going to reflect off. Okay, so that is your reflected ray. Okay, and these two are going to have angles that they come in at and angles that they leave at. Okay, so this would be your incident angle, so theta I, and then this would be your reflected angle, theta R. Okay, so whenever they come in, the law of reflection states that whatever the angle is coming in, the angle coming out is going to be the same. Okay, so like let's say if this was 30 degrees, that means the reflected wave will also be 30 degrees as well. Now, as soon as you enter a new medium, okay, so some of this light wave is going to reflect off, but some of it's going to go through, and I'm going to change up colors on that one. Okay, when you go from a less dense to more dense, it's going to hinder that motion, and it's actually going to pull that angle more close to the normal line. Okay, so if you notice my refracted ray, the angle is not as big. It's pulling that that refracted angle closer to that normal, which makes it smaller. Okay, so this would be your refracted ray, and this would be theta R. Okay, I just used a big case R there. It honestly doesn't matter which one you use. I'm just using lowercase and uppercase to distinguish the two. Okay, so that is when you go from less dense to more dense. Okay, so a couple of things happen there is you bend towards the normal. So your little bullet points down here, you bend towards the normal. And your angle of incidence is greater than the angle of refraction. That just means that your original angle is bigger than your new refracted angle. Okay, so that means that theta I is bigger than theta R. Now, the box over here to your right, you see here it says, how does velocity change? Speed of light. So if you actually notice, speed of light is slower and more dense material. And we talked about sound in the last bit of this packet. Sound loves dense material. Okay, so remember, a solid is the best for transferring sound. Liquid would be good, but not as good. And then gas is actually the slowest form for sound, because the whole purpose of sound is to transfer energy to the particle next to it. Okay, if you put those particles right near each other, that relay happens a lot quicker. Now with light actually has to be absorbed and emitted. So the more stuff you put in its way, it creates more and more delay because it has to be absorbed, then emitted, absorbed and emitted. It just keeps adding more and more stuff in the way. So light does not like dense material. It prefers, like, space would be the best case scenario. Okay, light travels the fastest in space because there's nothing in the way. There's no particles, anything like that. Okay, but sound needs that dense material, okay, to travel faster. So if you were to try to put it in space, it wouldn't even work because the particles aren't even there. Okay, so make sure you kind of know that. Now let's do the opposite scenario. So let's draw our surface again. Okay, so here's our water. Okay, let's say now we're going the opposite way. Okay, so we're going from water, and I'm just going to say the water is on top. I know it kind of looks upside down here. Okay, so we'll just say water's on top, so that's our dense, and then air is on bottom. Okay, so we're going from more dense to less dense. Okay, let's draw our normal line. Our normal line's going down. And let's draw our incident ray. So our incident's coming in. So this is our incident. Okay, it has its own angle. Okay, theta I. And then you have the reflected ray going out, and it's got his angle, so theta R. Okay, so nothing changed there. That's the same stuff, so both those angles are still the same. But now your refracted angle is going to be different. Okay, so when you go from more dense to less dense, the way I remember this is that you're going from something hard to something easy. So that light ray just kind of takes off. It goes away from the normal, so now it's getting further from the normal. So now you got this big angle here, so your refracted angle is a lot bigger than its original angle now. So this is your refracted ray. So that's one thing to know is when you refracted ray going from more dense to less dense, it bends away from the normal, and the angle gets bigger than the original angle. So theta R is now bigger than theta I. Okay, next one is angle of incidence equals 0. So let's draw my surface, and let's draw our normal line. Okay, so what's going to happen here when my angle of incidence equals 0, that means I'm not coming in at an angle, I'm basically just coming straight down. Okay, so what's going to happen is some of that is going to reflect right back up in the same way, so my incidence, my reflected, and then some of it's still going to go through. So it's going to be refracted, it's going to go into my new medium, it's still going to change speed. Okay, so it either slow down or speed up based off of density. If it's going into a more dense material, it's going to slow down. If it goes into a less dense, it's going to speed up. Okay, so there's really not a whole lot. So this is your refracted here. There's not a whole lot to know on this one. Okay, you have partial transmission, partial reflection. Transmission just means the part that went through. Okay, and basically there's 0 deviation, so meaning nothing really changed directions at all. And that's basically it for that one. Okay, now, how do we find the angle of refraction? So how would we figure out what our angle of refraction is? So that's the whole theta R if we wanted to calculate it. Okay, so we have Snell's law. Okay, Snell's law is Ni sine of theta I equals Nr times sine of theta R. Okay, so let me explain that equation. So basically, your N is called the index of refraction. It's basically how dense a material is, which affects how well light travels in it. So the higher the index of refraction, the slower light travels in that, because remember, light does not like density. So Ni, so this whole I right here, that's your incidence. That basically means that's your incoming, that's your original. Okay, Nr is your new refracted angle, the one that went through to the new medium. So I do get a lot of confusion on which one's Ni, which one's Nr. Ni is always the original medium that you came in with, and then Nr is always the new medium that you're leaving with. Okay, so we'll go over how to calculate Ni, and then sine of angle theta I. So theta I would be your incoming angle, and theta R would be your new refracted angle. Now, if you did want to calculate index of refraction, which is basically the density, how well light travels in it, what you do is you take c, which is the speed of light, and you divide it by the velocity, the new velocity of this light, or this light in that material. Okay, so c would be the speed of light in a vacuum, which would basically be space. So that means that is as fast as it would go. That's the whole 3.0 times 10 to the 8th. That is your max speed for light. Okay, and what you would do is you would divide it by the speed of light in the new medium that it's in. Okay, so let's say your speed of light in a piece of glass is 2.5 times 10 to the 8th. You would just take 3.0 times 10 to the 8th and divide it by 2.5 times 10 to the 8th. And that would basically give you your refractive index, or basically the density of the material and how well light travels in it. So here, again, it reflects optical density, so how dense it is, so how much is it going to slow down that light. Okay, so if N increases, okay, that means the velocity of light is going to decrease. Okay, so there's more stuff in the way. So let's look at an example. Light travels from crown glass into water. So I gave you the refractive indexes here. And then we will give you a box of refractive indexes. Okay, so if we don't mention it, okay, look on that box, and then you would have that, and then you'd be good there. Or you'd be solving for n, so we would give you the different velocities, but we'll do more examples on that later. So big thing here is you're going from crown glass to water. So your original is the crown glass, so this would be your Ni, and the water would be your Nr. Okay, now the angle of incidence, okay, so that's your I, in the glass is 40, so that means this is my theta I, my original angle that I came in with. So make sure you can label that because you want to be able to keep that with the right spot. So A, it says, will the light bend towards or away from the normal? Okay, so if you look at the densities, I'm going from 1.52 to 1.33. Okay, so that basically means I'm going from a more dense to less dense. And real quick, I'm just going to draw this over here. You don't really have to draw it, but remember we talked about when we went from a more dense, so more to less, what you had is you had your incident ray coming in, and it had its angle there. Now, when you go from more dense to less dense, remember that angle got bigger. It's going to go away from the normal. Okay, so now your theta R is going to be bigger. So that would be your answer. Okay, it's going to bend away from the normal. Now it says, what is the angle of refraction? So that means now we are looking for what is my refraction angle, so the theta R. Okay, so this, remember our equation is Ni sine of theta I equals Nr times sine of theta R. Okay, so Ni was 1.52 times sine of 40 equals Nr, which we don't know. Oh, no, actually we do know that. Sorry, it was 1.33. So 1.33. And then sine of theta R. Okay, that is the part we don't know right here. That's what we're looking for. Okay, so one, make sure you're in degree mode. Otherwise, you're going to get a wrong answer. And then mathematically, what I would do is I would solve the left side. So in my calculator, I would put 1.52 times sine of 40, get an answer, and then go ahead and divide that by 1.33 to get that off the side. And that'll give you 0.735 equals sine of theta R. Okay, now I want theta R, and that sine is in the way. So what I'm going to do is I'm going to bring that sine over, and when you do, it becomes inverse. So it becomes inverse sine, so sine with a -1. All you got to do is press second sine in your calculator to get that, and you put 0.735 in it, equals theta R. So now on your calculator, all you got to do is press second sine, 0.735, press enter, and you're going to get an angle of 47.31 degrees. So that is your new angle that it refracted at, which if you look, it actually revalidates what we answered up here. Okay, so remember we said it would bend away from the normal, which means my new angle is going to be bigger than my original. If my original was 40 and now it's 47.31, that matches. Okay, and that'll end that one.